Hi friends, uh, in this chapter we are going to design an analysis for an RCC retaining wall. There are two types of retaining wall, cantilever type of retaining wall and counterfort type of retaining wall. What is the purpose of retaining wall? To retain the earth, soil or water and what it may be. But here in this case we are only considering the soil for retaining from the retaining wall. Now, there are various conditions upon the type of retaining wall that depends upon the height of the retaining wall. Cantilever type of retaining wall is only applicable when the height is restricted up to 6 meters. When the total height of the retaining wall exceeds 6 meters, then it is uneconomical. Hence, at that stage, we have to use another type of retaining wall we call as a counterfort type of retaining wall. That is, the total height is greater than 6 meters. Now, there are various components for the retaining wall. Generally, we bifurcate into three types of components. Number one, the base. Number two, the toe, heel, and the stem. Base is also had bifurcated into two, that is toe and heel, and another is the stem that also we call as a vertical wall. So now we can see this is the toe, this is the heel, this is the base, and this is we can call as the stem. We call this as a stem. Now, before we design, we must understand the behavior of a structure when it has been loaded. What for it is required? Because we know that the concrete is strong in compression and the weak in tension. So we have to see the which portion of this retaining wall suffers from the tension and suffers from the compression. Because if it is suffering from the tension, then we'll have to provide the reinforcement in the tension zone. So we'll first of all go for the behavior, and then according to that behavior, we'll decide where to provide the reinforcement. First of all, we'll talk of the soil pressure over the vertical wall that we call as a stem. Water comes over here, it deflects like this, means the tension come on this face and compression on this face. So whenever we are talking of the behavior, we have to see that the tension is on the this face of the wall. So we'll have to provide the reinforcement toward this face. Similarly, when we are talking about this toe, then it is because of the upward pressure, it behaves like this a cantilever type of wall, cantilever beam, and the tension will be at the bottom and the compression will be at the top. So we'll have to provide the reinforcement in this portion at the bottom, main reinforcement. Similarly, about this particular part that is we can call the heel, it has got upward pressure as well as the downward force because of the soil over here. And finally, the net deflection comes out to be like this, fixed over here and free at this end. Again, you'll find that the tension will be at the top and compression will be at the bottom. So, when we are talking of the base, and especially we are talking about the heel, the reinforcement should be at the top of this uh, heel and not at the bottom as we have seen over here. That is the most important. Now, just to consider the analysis, we are considering some analytical data. Following data are to be taken into consideration. Following parameters are considered: bearing capacity as 200 kilonewton per meter square. Total height of wall taken as 5 meters. Weight of the concrete, that is R.C.C, taken as 25 kilonewton per meter cube. Unit weight of soil is 18 kilonewton per meter cube. Angle of repose of soil is 30 degree, and coefficient of friction between the soil and the concrete is taken as 0.7. And here, while considering, we are considering the soil over the wall is on the level, there is no surcharge. Now, consideration of parameters of the walls. How to decide the thickness, width, length, and other parameters of the components, retaining wall components. So, thickness of the base generally taken as 1/10 of the total height. Here, our total height is 5 meter, 1/10, that is 0.5 meter. And one important thing is, when we are talking of the thickness of this base is zero point 0.5, the same thickness is to be provided at the bottom of the stem also, so that our design will be safe. Now, thickness of the top is taken as say 0.3. You should not be less than 0.3 at any cost, and maximum that we have taken at the bottom as 0.5. Total width of the base is generally taken as 0.75 to 0.8. For safer side, I am taking it as 0.8 of capital H, that is 5 meters, that is 4 meter. Width of the slab, toe slab, will be 25% of the base width. Base width is 4 meters and 25% is 1 meter. So we can say that the width of the toe is 1 meter, total width of the base is 4 meter, with thickness of the stem at the bottom is 0.5. Definitely the width of the heel is 2.5 meter. Now the height of the stem is nothing but the total height minus the thickness of the base slab, which comes out to be 4.5 meter. We have to see about the active pressure and not the passive pressure at all. So considering active pressure taken as 1 minus sine of phi upon 1 plus sine of phi, phi is nothing but the angle of repose. Substituting this value of sine at 30 degrees, we are getting the constant as 1 by 3 or 0.33. Now, before we should go for design, first I will do further analysis of the retaining wall. For the analysis of the retaining wall, we are bifurcated the whole structure into number of components. Component 1, component 2, component 3, and component 4. First component is that of the stem, sorry, that of the base. Second is the vertical rectangular component of the stem. Third will be the triangular portion of a stem. And fourth will be the soil over the heel. Soil over the heel. Now, as we have already discussed, we are giving the total width as 4 meters. Total thickness of the base slab is 0.5 meters. This thickness is equal to this thickness. So this is 0.3. So this is 0.5. Automatically this comes out to be 0.2 meter. This total height is 5 meter, and the height of the stem is only taken as 4.5 meter. Now we'll make a prepare. We'll have to make a table and we'll place the details of all the required components as per the requirement. First of all, consider section number 1. Then is nothing but this length into this thickness into 1 meter along the length multiplied with the density of the concrete. That is 4 meter, 0.5 meter, 1 meter, and 25. So it comes out to be 50 kilonewton. The CG from this corner, we can call this O. CG from O is taken as half of that, that is 2 meter. And the overturning moment will be taken as or the we can call it the moment taken at this will be this load multiplied by the distance of the CG, which is taken as clockwise direction. It will be acting in this direction. So clockwise, which is taken as this into this is equal to. Now stem, I'm talking about the vertical portion. This is point 0.3, this is 4.5, this is 4.5 multiplied by 1 meter in this direction multiplied by 25. And its CG from O is at a distance of 1.35 meter, that is 1 meter plus zero point 0.2 meter plus half of 0.13, and it comes out to be 1.35, and this will be the moment. Third, this is the third section, half base into height into 1 into 25, and its CG right from here is taken at 1.132 meter, and the moment will be 12.735. Now we'll go for the wall. Sorry. Now we'll go for the another portion, that is fourth component, fourth section, that is about this one. So 2.5 into 4.5 into 1 into the density of the earth, which is taken as 18. And we'll find over here that is 2.5 into 4.5 into 1 into 18, and its CG at a distance of 2.75 from O. And if you add all this with the total weight acting downward, this is the total downward moment, which we can also call as the stabilizing moment, that is 715.17 kilonewton meter, and total downward weight is 347.5. With the help of these two parameters, that is sigma W and sigma M, we'll calculate the stability. So before should go for the stability, first of all we have to see the total horizontal force of the soil over the vertical wall. This height is 5 meter. This total height is 5 meter. Then pressure is acting over, the pressure goes on increasing, and the base is nothing but W into H. W is 18, H is height, 5 meter, that's 90 kg per meter square. Then the area of the triangle multiplied by, that is this, into 1 will give the total force acting over here, which is acting at a distance of 1/3 from the base, because the CG of the triangle is 1/3 from the base. And now we'll find that area of the upper pressure will be in the direction like showing like this, will be half base into height into active pressure component, that is 1 minus sine of phi upon 1 plus sine of phi, that way already it is 1 by 3, and it comes out to be 75 kilonewton. The CG acting over here, so we can say the total horizontal moment will be nothing but the total force into distance of the CG. And we see that 75 into 5 by 1/3 of 5, that is giving me 125 kilonewton meter is an overturning moment. Now, now summarizing all the results that we have just now calculated either through the table or by making some calculation through the soil moment. Sigma W 347.5, sigma M stabilizing moment 715.17 kilonewton meter, horizontal sliding force Sigma at the sigma h is equal to 75 kilonewton. Horizontal overturning moment is 125 kilonewton and coefficient of friction as 0.7. After calculating all the parameters now, we have to go for the various checks. First check is the check for sliding. Stabilizing force multiplied by the coefficient of friction divided by the overturning force should be greater than 2. Then we can say yes, it is safe for the sliding. It is safe for this way. Substituting the values which are shown on the above our portion over here like this formula. Now we are substituting over here. We can find this value will be 3.24, which is greater than 2. Check for overturning. Stabilizing moment upon the overturning moment. Definitely, stabilizing moment should be more as compared to the overturning moment. Means it should be greater than 1.5 as per the code. Then we can say it is okay. Yes. Over stabilizing moment is this much. Overturning moment is 125, 5.72, and which is greater than 1.5. So we can say yes. Our design is safe for the overturning moment. Also, the whole wall will not be overturned. Check number 3. Check for eccentricity. First of all, we have to find out the actual eccentricity, which is nothing but b by 2 minus sigma mw minus sigma mh upon sigma w. All the parameters should be less than one third of the b by 2, or we can call it as a middle third rule. Middle third rule. So actual eccentricity should be less than the middle third rule of width by 2 multiplied by 1 by 3. So now 4 is the width, 2 sigma m minus sigma mh upon sigma w should be less than one third of 4 by 2, and this comes out to be 0.30 is less than 0.66.30. So we can say eccentricity is less, actual eccentricity is less than the required eccentricity, which is following the consideration of one third b by 2 or a middle third rule. Check for maximum pressure. Under any circumstances, we have to see that the maximum pressure should not exceed the bearing capacity of the soil. Otherwise, whole structure will sink in the soil. So now, using the mathematical expression for maximum pressure, sigma W upon B into 1 plus 6 E by B, where E is nothing but the actual eccentricity, B is the width, sigma W at 347 that we have already 347.5 that we have already seen. Substituting these value, we find that the value comes out to be 125 point something, rounding it off on the other side is 126 kilonewton per meter square, which is less than 200 kilonewton meter square. We can say it will not be penetrated. So this wall that we have designed is safe, and it can bear the soil can bear that much pressure over here. Similarly, we'll go for the minimum check. Under any circumstances, we have to see that for easiness of design, we have to see that there should not be any tension in the bottom portion of a retaining wall, that is the base. Otherwise, it may create a problem, and additional reinforcement and other activities are to be carried out. Hence, we have to see that under any circumstances, minimum pressure should always be greater than zero. That is, it should not comes out to be should not give a negative sign. It should not give a negative sign. So P minimum is nothing but instead of plus minus, I have to put this as minus only. Previously for maximum pressure it was plus. For minimum pressure it is minus, and it should be always greater than 0. And we find substituting sigma W, E and B, we find it comes out to 47.78 kilonewton per meter square, which is greater than 0. We can say the no tension at the base and the design is safe. So we have designed all such type of checks that has been applied so far, and we see that our retaining wall dimensions that we have decided by considering the width, thickness, etc., is such that it observes all the required checks, and which is passes all the checks so far, and our design is safe. After this, the most important is after the application of the checks, and after satisfactory uh, application of the check, all the five checks, then we'll go for the design of a cantilever type of retaining wall. First of all, we'll go for vertical wall, we call the stem. It is considered that it is fixed at base and this is vertical wall. Now upward pressure, the soil pressure coming from here will behave like this up to 4.5 have 5 meter, because below that there will be a base slab, that is 2 V, that is the base slab. So the total pressure will be as usual. Instead of 5 meters as we have taken previously, it is WH square by 2 into 1 minus sine of y upon 1 plus sine of y. Phi will be as usual taken as this much whole taken as 1/3. W, that is the unit weight of a soil. Height is the total height like this. It comes out to be 75, 6.60.75 kilonewton. Maximum moment nothing but 1/3 of this into total force. P into x bar, that is h by 3. And the total maximum moment at the base of the stem or vertical wall is 91.125. Rounding it off on the higher side, say 100 kilonewton meter. So design moment will be 1.5 times 100, that is 150 kilonewton meter. Now, after we could find out the maximum bending moment, now we'll design the depth. And we have to see that this depth required should always be less than the depth or thickness that we have provided for the base slab, for the vertical wall, and it is we have taken as 500 mm. Just see now. Using D required is equal to mu max upon R into B. R is equal to 0.138 into FCK, because characteristic strength of concrete that we have taken as 20, and hence it is, and B will always be taken as 1000 mm, being a slab. So D required comes out of 233.12. This is the required effective depth. What is the effective depth actually we have provided? Considering 16 mm bar diameter, overall depth minus the clear cover minus half the bar diameter. I am considering 16 mm bar diameter in the beginning. If we find it is insufficient, then accordingly we will change it. But at this stage, I am considering that main bar applied is 16 mm. Now, this is the total thickness of this vertical wall. Minimum cover as 20 mm, and half the bar diameter. This will be nothing but the effective cover. It comes out to be 470 mm, which is greater than 233.12 mm. So required is less or provided is more than required. So for depth purpose, we can say it resists that much moment. So we are going clear. Now after this, we can go for the finding out the area of steel. Using the empirical formula, you can use the other formula which is given in IS code 456/2000 in page number 96. In that also, but it has to be a quadratic equation, so I am avoiding that. I am giving that empirical formula where FCK is 20, FY is 415, MU max that we everything is known, B is 1000, D we have to take D as 478. Substituting this value, we find that area comes out to be 920.44, rounding it up on say 950 mm square. Now considering the 60 mm bar, we have just calculated it comes to 210.5 mm center to center, and rounding it on the lower side, not on the higher side at all, it will be taken as 200 mm center to center. So we'll have to provide the 16 mm bar vertical bar along the inner face of a retaining wall toward the soil face vertically, and it is placed at a spacing of 200 mm center to center. Similarly, we have to find out the distribution steel. As per the code, of distribution steel is 0.12% of the gross cross sectional area, and it comes out to be 600 mm square. Assuming 12 mm bar, area of steel of one bar is 113, and the spacing can be calculated as a small area of steel upon capital S into 1000. Rounding it on the lower side, spacing is to be reduced, not to be increased. Not to be increased. So say 150 mm center to center. This is all the design of a vertical wall, we can also call as a stem. Now we'll go for the design of toe. Now, just see, total width is 4 meter. This width of the heel is 2.5 meter. This is the base of the stem, zero point 0.5, and this is 1 meter. Almost the pressure is coming from here, and we are neglecting the soil over above the toe. Now we have to see the pressure diagram. This is the maximum pressure. This is the minimum pressure. Now at this junction of this stem and an toe, I have to find out the component of the pressure diagram over here. And once we can find out this pressure diagram using this trapezoid, with a maximum ordinate as 126 and minimum ordinate as 48 and total distance as 4 meters. Now we can find, if we can find out the value, then we have to find out the CG of this from here. CG of this pressure diagram, that is the force acting from here, and that will find the moment which is acting upward in this direction, that we have seen in the beginning also. Now we can see this is the area of the pressure diagram, that is the force. This is the CG, that is A1 plus 2 A plus 2B upon A plus B into H by 3 or X by 3. That will give the value of X bar. Maximum upward moment will P into X bar. That comes out 59, rounding it up, say 60 kilonewton meter. That we have already seen. This is the upward pressure from the soil. So we'll have to provide the reinforcement at the bottom of the toe slab, main reinforcement. Now for that, we are just calculating the area of steel using the same empirical method. Formula, here mu max will be 60 kilonewton meter, and D will be same as 478. Mu max will be there, and we find that AST comes out to be 576. Now say rounding it on 100, say 600. Now using providing the 12 mm 5 bar at the rate of 150 mm center to center, that we already calculated previously, keeping the same parameters, and the distribution still will be the same as we have done already, because the total thickness is zero point 0.5. Total thickness is zero point 0.5. Now the design of the heel. The design of the heel. Now there are two types of loads. One, upward pressure, and another, the downward weight of the soil. So we take it two into consideration. First of all, we only calculate the moment because of the upward weight of the soil above this heel. Then taking the moment at the junction of the stem and the heel. This point. First of all, calculate this ordinate as well as calculating the ordinate over here. Similarly, calculate this ordinate over here. Then find the CG from here and pressure diagram of this much portion, that is F E H G F. This is the pressure diagram. Take the area, find out the CG, take the moment. This will give the upward pressure and upward moment. Similarly, this length above this, there is a soil. We find out the total load and take the moment, and we find upward pressure for that ordinate, that will calculate 96.75. Here I am talking about this point. Now x bar will be a plus 2b upon a plus b into x by 3. That will be the value of x bar. Moment will be, it is acting upward, so it will count as a negative one. So it comes minus 231.59 kilonewton meter. Now, downward bending moment due to the weight of the soil over the heel, which is nothing but the density into 1 meter length into 4.5 meter. This is uniformly distributed load. This is the fixity at the junction of the stem and a base. This is the, you know that the width of the heel is 2.5 meter and it is comes out to 81 kilonewton per meter. Maximum bending moment WL square by 2. L will be now here 2.5 and W will be 81. WL square by 2 will be the maximum bending moment, which is acting downward. We consider this as positive. Say, then the net bending moment will be the positive bending moment minus the negative bending moment. It comes out to be the final bending moment, and we'll find it comes out to be 21.53 positive, rounding as say 25 kilonewton meter. Because it is only 25 kilonewton, but acting positive means it is acting downward, so we have to provide the main reinforcement at the top of the uh, base slab, that is at the heel, not on the bottom. Now, considering this moment, we can find out the minimum 12 mm bar, and we can find out the distribution steel same as that of the stem that we have calculated, same as that of we have calculated for the toe also, and the same will be provided at the heel, because everywhere we find that the thickness, overall thickness remains the same, that is 500 mm. So 0.15 it automatically comes out to 600 mm square. Now we'll discuss something about the reinforcement. After designing all this, we can see this is the 16 mm for at a spacing of 200 mm center to center over the entire length, and this is the distribution steel which is taken as 112 mm bar at 150 mm center to center. Similarly, as we have seen, we'll have to provide the main reinforcement for the toe, which will be over here, which is 12 5 at the rate of 150 center to center. Similarly, for the here we have to provide the reinforcement, main reinforcement over here, same as 12 5 at the rate of 150 center to center. So everywhere you will find that these two bars are showing the 12 bar have 150 center to center. Except this wall, vertical wall having 16 bar meter at the rate of 200 center to center. So this design part is over. Now summarizing the whole design, we say the top width of the stem is 0.3, bottom width of the stem is 0.5, total width of the base is 4.0, total thickness of the base slab is zero point 0.5, and reinforcement has already been shown over there. In this way, we can complete our whole design. That's over and all. Thank you very much for giving the patience hearing so far.